Hi guys, I'm broadcasting from my office now in the science building. I'm sorry we're not in the classroom together. I wanted to create some videos working from where we left off with indeterminate forms and L'Hopital's rule. So starting with this example here and starting, let's see, more broadly with specifically the indeterminate forms 0 over 0 and plus or minus infinity over infinity. So remember I was saying the last time we met a couple of weeks ago that those forms are sort of a good news, bad news situation. You cannot determine the limit when it's in one of these forms. That's the bad news. The good news is we have L'Hopital's rule that can help out in these situations, which is fairly straightforward rule to use. So starting with this one here, I'm going to get a colored marker. I'm going to ignore my face on the screen there. So starting by analyzing the form of this limit, you don't want to hit these limits right with L'Hopital's rule without verifying that it's in one of those forms. If it's got the form, say, 5 over 0, L'Hopital's rule does not apply, and you're going to get the wrong answer if you try to apply it. So checking the form first. So I'm substituting 0. 2 to the 0 is 1. Any non-zero number to the 0 power is 1. Minus 1, so I have 1 minus 1 on top, that's 0, and then 0 for x on the bottom, so 0 over 0. Which means, yes, we can apply L'Hopital's rule. If we do that, then this becomes the limit as x approaches 0 of, okay, so let's do the easy part first. Derivative of x is just 1. You may recall from Cal 1, or you may have forgotten, that, let me jot it down over to the side here, the derivative of an expression of the form some constant raised to the x is natural log of the base times a to the x. So the derivative of 2 to the x is natural log of the base times 2 to the x minus the derivative of a constant is 0. So we've taken the derivative of the top and the derivative of the bottom independently when you apply L'Hopital's rule. Notice that now if I substitute 0, I no longer have that indeterminate 0 over 0 form. Now if I plug in 0, I have natural log of 2 times 2 to the 0 all divided by 1. And again, remember, so non-zero number raised to the 0 power, this is equal to 1. And so this is equal to natural log of 2. So in this case, L'Hopital's rule gives us a limit of natural log of 2. Let me see if I can get another example below this one. So a second example, and I'm using the examples from the printed notes that I posted for you. So the limit as x approaches infinity of 2x plus 5 over 3x squared minus 1. Now, fastest way to evaluate this limit is to use shortcuts that you learned in Calculus 1. For a rational function, which is polynomial over polynomial, we can, limits at plus or minus infinity, we can compare the degrees of the numerator and denominator. Whenever you have a larger degree in the denominator, this limit at infinity is automatically 0. And that's the best way to determine this limit. However, L'Hopital's rule does apply in this case. So just as another demonstration of L'Hopital's rule, first if we check the form, remember you don't want to just apply L'Hopital's rule willy-nilly without making sure that it's applicable. So in this case, as x approaches infinity, this numerator grows without bound. This is the numerator approaches infinity. Denominator 3 times a really big number squared, that's going to be a really big number. Minus 1, who cares? That becomes virtually, 0 as x approaches infinity. So this thing has the form infinity over infinity, which means yes, L'Hopital's rule does apply. And so the limit as x approaches infinity, if I take the derivative of the top, that's 2. If I take the derivative of the bottom, that's 6x to the first. Now this limit has the form, can I write down here? Yes, it looks like it shows up. Okay, now this limit has the form finite number over infinity. And limits of that form always go to 0. So there we see that L'Hopital's rule gives us the same answer. However, it's still going to be really helpful for you to remember those rules about limits at infinity for rational functions. That's going to come up a lot in Chapter 9 as well. And so L'Hopital's rule is going to take extra time, especially if the degrees were higher here. You'll run into cases where you're applying L'Hopital's rule over and over, and you can get the answer eventually, but it's much better to just remember those rules they're printed in the notes with this section.